Vitali's covering theorem gives us a way of effectively partitioning a set A using balls from a specified collection, so long as we're able to partition A up to a set of measure 0, and so long as the collection of balls that we're using is sufficiently large. More specifically, Vitali's covering theorem states the following. So suppose we have a radon measure mu, a subset A of Euclidean space, and a collection of closed balls such that for any point in the set A, we can find arbitrarily small balls centered at that point. Then we may find a countable subcollection of balls that cover A up to a set of mu measure 0. So I'll give a proof of this in pictures, and I'll assume that the set A is bounded so that we can use the Besicovitch covering theorem. So recall that the Besicovitch covering theorem says that we can find collections of balls. So we can find n collections of balls such that each collection Bi is a collection of disjoint balls, and so that they cover the set A and they have bounded overlap. Okay, so if I integrate this, I have that mu of A is at most the sum from I equals 1 to n of the integral of the sum of B in Bi of the characteristic function of B. And notice by the bounded overlap property, the sum of these characteristics functions of balls is no more than a constant c. So this is at most the sum from I equals 1 to n of the integral of c over the union of the balls in this collection. Okay, or in other words, just the sum from I equals 1 to n of c times the measure of the union. Okay, so notice then, essentially by a pigeonhole principle, we know that there exists an I such that mu of A divided by nc is at most the measure of the union of balls from this collection. Okay, so what this means is that these disjoint collections that make up our Besicovitch subcover, one of them takes up a very large chunk of the set A, so 1 over n times c percent of the set. So what we're going to do then is just isolate that particular subcover. So this one contains a large chunk of A with respect to mu. Furthermore, it's not hard to show that we can remove a few of these balls so that we have a finite collection that still covers, let's say, 1 over 2nc percent of the set. Okay? So in other words, we can find a finite collection of disjoint closed balls that intersects a fixed percentage of the set A in measure. So now, because it's a finite collection of balls, if I look at disjoint closed balls, if I look at the complement of those balls, I get an open set. And because of this condition, that at every point in the set A I can find arbitrarily small balls, that means that for the part of A in the complement of this finite union, I can find a covering of the remainder of A using balls that are disjoint from these red balls. Okay? So then, by the Besicovitch, so suppose that this is the collection of balls that I get, just by looking at balls from my collection that are centered on A outside of these red balls. Now, by the Besicovitch covering theorem, I can now find a subcollection from these balls that have bounded overlap and still contain A, and so that I can split them into subcollections, and many subcollections, each one of which is a collection of disjoint balls. Okay, and then again, I can do the exact same argument as before. I can take one of these collections and then trim it down to a finite number so that it still intersects this fixed percent of the remainder of A with respect to mu measure. Okay, so now if I looked at the part of A that's not inside either the red or the green balls, notice that the measure has decreased by the same factor twice now. So if, for example, the red balls contained alpha percent of A, that would mean that the remainder, the stuff outside the red balls, contained 1 minus alpha percent. And now the part outside the red and green balls has 1 minus alpha squared percent of the original measure of A. And then I just keep repeating this, and in the end, I'm going to get a collection of disjoint closed balls that contain mu almost all of the set A. In the next video, we'll discuss how to use Vitali's covering theorem to study differentiation of measures.